Take a moment. Look up at the night sky. Really look. It's a vast, dark canvas, an endless expanse punctuated by the distant light of stars, each a sun potentially nurturing its own family of planets. Think about the sheer scale of it all. We often imagine planets as variations on what we know, rocky worlds like Earth or Mars or gas giants like Jupiter. But what if, hidden in that darkness beyond our solar system, there were planets made not of rock or gas, but of diamond? A solid, glittering sphere of pure, compressed carbon. Imagine mountains of pure, crystalline carbon, towering peaks that catch the light in extraordinary ways. Imagine the effect of a sun's rays hitting that surface, scattering starlight into a billion rainbows, a dazzling display of light and color unlike anything we've ever witnessed. And what about the liquids? Oceans of exotic liquids, perhaps methane or other hydrocarbons, bubbling and swirling over diamond shores, creating an alien coastline. This isn't just science fiction dreamed up for a fantastical story. It's a real possibility that modern astronomy has uncovered, based on sound scientific principles and observation. The universe, in its infinite creativity, using the same basic elements as Earth, creates worlds that defy our expectations, pushing the boundaries of what we consider possible. It's a cosmic laboratory of endless experimentation. Diamonds on Earth are rare, highly prized for their beauty and durability. They are symbols of beauty and power, formed deep within our planet under immense pressure and heat, a testament to the Earth's geological processes. Now scale that up. Imagine an entire planet where the very crust is diamond, a solid, shimmering surface stretching across continents. It's a concept both scientifically thrilling, sparking our curiosity about planetary formation, and profoundly romantic, a glittering jewel in the vast darkness. It's a reminder that the cosmos holds wonders beyond our wildest dreams, challenges our assumptions, and inspires us to keep exploring. The story of the Diamond Planet begins not with a discovery but with a simple question, a fundamental drive to understand what's out there, lurking in the inky blackness between the stars. As our tools improve, as telescopes become more powerful, and our analytical techniques more sophisticated, we're not just finding planets, we're finding a bewildering variety of them. We're discovering their character, teasing out the secrets of their atmospheres, and determining their composition with increasing accuracy. And sometimes, just sometimes, what we find is stranger, more unexpected, and more awe-inspiring than we ever imagined possible, challenging our understanding of planetary formation and the very nature of the universe. Our story begins with a wobble, a subtle, almost imperceptible tremor in the vast expanse of space. It's a story of meticulous observation, cutting-edge technology, and the relentless pursuit of knowledge that defines modern astronomy. A tiny shift in the light of a star called 55 Cancri, a seemingly ordinary star yet harboring secrets that would challenge our understanding of planetary formation and composition. Just 41 light-years away, close enough for detailed study, yet still a journey of unimaginable scale. This proximity makes 55 Cancri a prime target for astronomers seeking to unravel the mysteries of exoplanets. Astronomers use the radial velocity method, a technique that allows them to detect the presence of unseen planets by measuring the subtle wobble they induce in their host star, detecting the gravitational tug of orbiting planets, a delicate dance of celestial bodies, each influencing the other through the invisible force of gravity. These minute variations in stellar velocity provide crucial clues about the mass and orbital characteristics of the planets. In 2004, after painstaking analysis and countless hours of observation, they found something extraordinary, a planet unlike any they had encountered before. 55 Cancri e, a super-Earth, a class of exoplanets more massive than Earth but lighter than gas giants like Neptune. Twice Earth's size, a considerable difference that hints at a vastly different internal structure and geological history. 8 times its mass, making it significantly denser than our home planet, and raising intriguing questions about its composition, and far too dense to be a gas planet, defying conventional models of planetary formation, and challenging scientists to rethink their assumptions. What's more, it orbits its star in just 18 hours, a blistering pace that defies our earthly sense of time and seasons. 1 year shorter than a single Earth day, a truly alien concept that underscores the incredible diversity of planetary systems in our galaxy. One side faces perpetual daylight, bathed in the intense radiation of its nearby star, a landscape of unimaginable heat and light. The other, eternal night, a frigid, dark realm where the sun never shines, creating a stark contrast between the two hemispheres, both scorched by unimaginable heat, temperatures reaching thousands of degrees, far exceeding anything found on Earth. The discovery was a triumph of precision, pieced together from years of data, a testament to the dedication and ingenuity of the scientists involved. 55 Cancri E wasn't just another planet, it wasn't just a blip on a graph or a data point in a spreadsheet, it was a puzzle, a cosmic enigma that demanded explanation. Its size, mass, and orbit hinted at something never seen before, a new class of planet with properties that defied existing theories. Scientists asked, they began to probe deeper, driven by an insatiable curiosity to understand the nature of this strange new world. What is this world made of? What secrets does it hold beneath its scorching surface? The answer would be even more spectacular than its discovery, revealing a planet of unimaginable wealth and sparking a scientific debate that continues to this day. Imagine a planet, not of rock and water, but of pure, unadulterated diamond. How do you get a planet made of diamond? What cosmic recipe could possibly yield such a dazzling world? It starts with chemistry, the fundamental building blocks of the universe and the interactions between them. The specific chemical composition of the materials that coalesce to form a planet is key. Our solar system, and the planets within it, formed from an oxygen-rich cloud, a swirling nebula of gas and dust left over from previous generations of stars. This abundance of oxygen led to the formation of silicate-based minerals, resulting in the rocky planets we know and love, like Earth, Mars, and Venus. But the exoplanetary system of 55 Cancri, located about 40 light-years away, is a different story. It's a system remarkably rich in carbon, an element with incredible bonding versatility. In such a carbon-rich environment, planets there could form from carbon compounds, a stark contrast to the silicate-dominated formation in our own solar system. Instead of the familiar silicates, these planets could be composed of graphite, silicon carbide, exotic materials not typically found in large quantities on Earth. This means that the building blocks of these planets are fundamentally different, composed of carbon-based materials rather than silicates. 55 Cancri E, one of the planets in the system, boasts 8 times Earth's mass, making it a super-Earth with immense gravitational forces at play. Given its substantial mass, 55 Cancri E's interior pressure would be immense, far exceeding anything found within our own planet. Under such extreme conditions of pressure and temperature, the very nature of matter can be transformed, leading to unexpected and fascinating results. And here's where the magic happens. Carbon, subjected to this intense pressure, transforms into diamond, the hardest naturally occurring substance known to humankind. The result, a planet unlike any other we've ever seen. A thick diamond mantle, a vast expanse of crystalline carbon stretching deep into the planet's interior. This diamond mantle is layered above an iron core, a dense metallic heart at the planet's center. And finally, with a graphite crust, a surface layer of carbon that gives the planet its outermost shell. A world built from the same element as life on Earth, carbon, the backbone of all known organic molecules. But instead of forming DNA and proteins, it's forged into the hardest substance in the universe, a testament to the incredible diversity of planetary formation. The reality of 55 Cancri E is far from idyllic. Its day side bakes at over 2,400 degrees Celsius, hot enough to vaporize metals. The ground glows with heat. The air is a thick, toxic soup of vaporized carbon. Volcanic eruptions could spew molten diamond or graphite. One side faces endless day, the other endless night with winds whipping at supersonic speeds. The night side is still hotter than any place on Earth. Permanent storms rage across the planet, scouring diamond mountains and graphite valleys. It's a treasure chest sealed by the very fires that forged it. The dream of walking on a diamond planet is destined to remain a dream. 41 light-years is an uncrossable gulf with current technology. Even if we could travel instantly, the planet's radiation, gravity, and heat would destroy any probe or lander. The atmosphere is a superheated, toxic barrier, the surface a glowing, molten landscape. No material we know could survive the descent. 55 Cancri E is a fortress, its treasures locked away by distance, radiation, and fire. We can only observe it from afar, decoding its secrets through starlight. It will forever remain a glittering jewel seen only through telescopes. Is 55 Cancri E unique? Maybe not. Carbon-rich stars exist throughout the galaxy, so diamond planets could be common. We search for them by measuring size, mass, and density. High density hints at carbon worlds. Spectroscopy lets us analyze atmospheres for carbon compounds. Some super-Earths we've found may already be diamond planets. As technology improves, we'll map not just planets but their compositions. The universe could be filled with exotic worlds, lava, water, and diamond alike. The search for these worlds is a quest to understand the full range of cosmic possibility. The idea of mining a diamond planet is tantalizing but pure fantasy for now. If we could bring back even a fraction of 55 Cancri diamond, the market would collapse. Diamonds would become as common as gravel, used for industry, not luxury. The real value of such discoveries isn't economic, it's in expanding human knowledge. The universe isn't ours to exploit, but to understand. The diamond planet is a shining reminder of the cosmos's mysteries. And our curiosity, the drive to know what lies beyond, is the most precious resource of all.